endocrine gland that we are going to talk about is adrenal glands. Now, adrenal glands are specifically glands which are present above the kidneys. So, these are two glands, each present, or rather a pair of glands, each of them present on the surface of the kidney. Right. Now, these adrenal glands, they are also, that's why, because they are present on the kidney, they are called as suprarenal glands. They are suprarenal glands. They are pyramid shape and they have a height, they have approximately a height of about 3 to 5 centimeters, 3 to 5 centimeters of height, and they have a width of, they have, let us say, a width that ranges from 2 to 3 centimeters in adults, in an average healthy adult. Okay. Now, when we cut the adrenal gland, we see that it is made up of three parts: the capsule, the outer capsule, the second adrenal cortex or the cortex, and the innermost medulla. Now, the peripheral tissue is the adrenal cortex. This is the adrenal cortex, and they say that the adrenal cortex is mesodermal in origin, whereas the innermost region, the tissues of the innermost region of the medulla, they are ectodermal in origin. So, the purple one, this purple outermost layer, I'll use the same purple. The purple outermost layer is the capsule. Okay. Then I have the innermost layer, which is the medulla. This is the innermost layer, which is the medulla, and surrounding is the cortex. Now, if I take a section cutting, means if I cut one area like this, if I take a sector cutting like this of the medulla, then when I look at it in the microscope, they are present in multiple layers. Okay, let me show them. So when I take that microscopic section cutting, as I said, the existing layers can be further divided into many sub layers, right? So you have the outermost capsule, and you have the innermost medulla. But the cortex layer is again divided into three sub-layers. You have three sub-layers of the cortex. The first one is the zona glomerulosa. The second one is the zona fasciculata, and the third one is the zona reticularis. So the cortex layer is again divided into three sub-layers, right? So this is the histological section, that is where you can see the cells in real life in different visuals. So this is the adrenal capsule. This region is the zona glomerulosa. This region. Then this region is represented by the zona fasciculata. So till here is the zona glomerulosa with more tightly present cells. The zona fasciculata comparatively have loose tissues, or the tissues are not very tightly held. Maybe it's a loose tissue. And the zona reticularis here. And finally, you have the lower adrenal medulla. Now, each area of the cortex, each subzones or the sublayers of the cortex, they are also useful in producing many hormones, which are also called as corticoids. So these, whatever hormones that are coming from the adrenal cortex, they are called as corticoids. They are called as corticoids because they are coming from the adrenal cortex. Okay, so let's see what are those. So as we've discussed, the adrenal cortex and even adrenal medulla will also secrete hormones. First, we are going to talk about the hormones that are secreted by the adrenal cortex, and it is called as corticoids, which are basically steroids. Now, the zona glomerulosa, it produces the mineral corticoids. The zona fasciculata produces the glucocorticoids, and the zona reticularis, it produces the androgens. So let us see the function of each. The mineralocorticoids, they are mostly, the main mineral corticoid that is produced is aldosterone. Now this aldosterone, its main level is, it is used to maintain the electrolytic and water balance. So basically it is useful in maintaining the osmotic pressure. It is useful in maintaining the osmotic pressure in both blood and urine. It is useful in blood, and when it is maintaining in the blood, simultaneously the result will be shown in the urine. So when it is maintaining osmotic pressure, then that means simultaneously it is associated with blood pressure and even blood volume also, because osmotic pressure controls the volume of water in the blood and in the urine, right? So what aldosterone does is it acts on the renal tubules. So this part is the renal tubules here. So the renal tubules, and it helps in the reabsorption of sodium and water from the renal tubules and excretion of potassium and phosphate ions. So this aldosterone, its secretion is stimulated by angiotensin 2 when blood pressure falls. Now this aldosterone, it belongs to an entire huge pathway called as the RAS pathway. You have a pathway, you will see it when you uh, we have discussed this in the excretory system chapter. If you want, you can go there and refer it. So the RAS pathway is the renin angiotensin aldosterone pathway. Aldosterone pathway. So these three different enzymes and hormones, they work together during the high blood pressure and low blood pressure to maintain the electrolyte balance of the blood and also that of urine. Okay, so that's why it's called as a salt saving hormone, because what it does is when there is low blood pressure, that means your blood needs more amount of salts. So what this hormone does is it forces the renal tubules to resend whatever salt that it has removed from the blood, whatever sodium ions it has taken from the blood, back to the blood. And when blood is taking sodium ions, its solute pressure is increasing, so it will take more water. So as a result, it elevates the blood pressure. It also helps in the maintenance of the electrolyte content, as we have discussed, body fluid volume, blood pressure, and aldosterone not only retains it but also helps in the excretion of potassium, which is comparatively a very harmful substance. Then so potassium and phosphate ions, it is excreted by the kidneys, whereas sodium ions and water, they are absorbed by the kidneys and sent to the blood. Now this also has a role in removing excess protons. It removes excess protons or hydrogen ions from urine. Right. So what it does is it prevents and it also removes excess ions or potassium ions from the blood also. So basically blood's pH should be at a particular level. Right. More than that, it is dangerous. It results in acidosis. So it makes sure that there is no blood and urine acidosis that is happening here. Okay, then the zona fasciculata basically produces glucocorticoids, and these glucocorticoids, they help in the carbohydrate metabolism, and the main one is cortisol. Cortisol is a very important corticoid. In fact, 95% of the glucocorticoids is cortisolic in nature. Other than that, it also produces corticosterone and cortisone. Corticosterone and cortisone. These are life-saving hormones. They're very, very important. Basically, it's people who are having anaphylactic shocks, people who are having low blood pressures, people who are on the verge of collapsing, even athletes. You hear that the athletes have taken steroids, or that fellow has taken steroids. What is the steroids? Steroids are nothing but these glucocorticoids that they take. What it does is it increases carbohydrate metabolism basically, and it gives us more energy. Then how does it impact on cellular metabolism? Carbohydrates, proteins, fats, basically it creates a combination called as gluconeogenesis, and it increases the catabolism of proteins, that is breakdown of proteins. It creates the breakdown of fats. Basically what it does is, not only is it creating the carbohydrate metabolism, it is creating gluconeogenesis, that is production of glucose from proteins and fats. It is also creating lipolysis, that is breakdown of fats. It is creating proteolysis, that is breakdown of proteins. It also has a major role in stress resistance. Cortisol also plays a very important role in the maintenance of the cardiovascular system and the kidney functioning. Right, it is also involved in the anti-inflammatory reactions and suppresses the immune and organ system. See, basically what it does is it depresses the immune system. Basically these glucocorticoids, they are given for patients who are undergoing organ transplant or who have suffered severe immune inflammatory, that is, they have suffered severe immune reactions. Okay, now when we were talking about epinephrine, I have told you that people have something called as an EpiPen, which acts as a life-saving drug. As soon as you have you have an inflammatory reaction, if you're injected with epinephrine, it acts very quickly and it releases the inflammation. Now that is a quicker response. The more delayed and more substantial anti-inflammatory response is given by glucocorticoids like cortisol. In fact, cortisol, commercially it is called as hydrocortisone, which is used for a lot of anti-inflammatory things. Like if you say you have a rash as an allergic reaction, like this poor little kid, so you are given hydrocortisone creams, topical creams, that you apply on the body of the child so that the reaction dies down. Similarly, cortisols and cortisosterones, they are given to people who are undergoing organ transplant, because their organs will show deep level of organ rejections as a reaction to immune response, right? So to prevent that, they do it. And how are they doing it? Basically they inhibit WBC production also. They reduce inflammation by inhibiting the action of the WBC, and as a result these are useful for the treatment of the they're very useful for the treatment of the rheumatoid arthritis also. Okay, now the adrenal medulla, as we have discussed, along with the cortex, even the medulla also secretes the hormones. It produces two hormones, adrenaline, which is the epinephrine, and noradrenaline, which is the norepinephrine. Now 80% it is epinephrine and 20% it is norepinephrine, and these are produced by a special group of cells in the adrenal medulla, which are called as chromaffin cells. So chromaffin cells are a group of cells, that special cells in the medulla, which produces these two hormones. These are also called as ketolkamines, ketocolines or ketolamines, different names. Okay, now chemically ketolamine. Now these hormones, they are basically secreted in the stress condition. We all know that adrenaline hormone is called as the fight or flight hormone, right? When you are worried, either it will give you the tendency to fight or just run away from there, right? So it's an emergency hormone. It increases the alertness of the body, pupillary dilation, piloerection, sweating. Piloerection is the standing of the hairs of the on the body, right? Sweating, dilation of the bronchioles, because when you are having increased alertness, that means your heart rate is beating more faster, so that means you need to take more oxygen, so your breathing also becomes erratic, right? This and adrenaline and or noradrenaline, they act on the circulatory system by increasing the heart activity, increase the blood pressure, increase the cardiac output, increase the respiratory rate, and all of this. And these hormones, they also stimulate the breakdown of glycogen, proteins, and fats. Basically it is creating glycogenolysis, gluconeogenesis, both cases to release more glucose, and that more glucose is further broken down to release more energy. So they help in the increase of the blood glucose level, which can be used as energy to either fight or flight, either to fight the battle or just run away. Even running away needs a lot of energy. So during the emergency, piloerection, sweating, dilation, and pupils are due to thyroxine, insulin glucagon, ketolamines, or corticoids. The answer is ketolamines. Adrenaline and noradrenaline do not promote. breakdown of proteins, breakdown of lipids, glycogenesis, and glycogenolysis. What do not, or what does it not promote? It does not promote glycogenesis. Okay, it does not promote the conversion of glucose to glycogen. Rather, it helps in the breakdown of the glycogen. Okay, the main glucocorticoid is insulin, glucagon, cortisol, or aldosterone. It is cortisol. Right, now let us go to the next gland, that is pancreas. Next we'll go to pancreas. Now pancreas is actually a mixed organ. It is both heterocrine and endocrine in nature. Means it's the same organ that has exocrinic activity where the secretions are moved through ducts, and endocrine, which is a ductless, where the secretions are directly released into the bloodstream. Now, pancreas is the small leaf-like elongated organ which is present just in the stomach, just below the liver. Right. Now, we have seen in the digestive system chapter, the chapter of digestion and absorption, we have seen how there is these ducts which come from the liver. It combines with the pancreas and joins into the small intestine, right? So the secretions of the pancreas, they move exocrinically through this duct called as pancreatic duct. Okay, now the pancreas contains two type of cells. The first type of cells that are shown here in this arrow, this is called as the clusters of acini. It is called as clusters of acini. Okay, now these clusters of acini, they are basically exocrinic cells. These are exocrinic cells whose secretions, which form what is called as the pancreatic juice, they enter into the small intestine using a duct called as the pancreatic duct. Okay, whereas the other type of cells that are seen here, these are called as the islets of Langerhans. Islets of Langerhans. Now these are the cells which are endocrinic in nature. These are the endocrine cells of the pancreas, which is the islets of Langerhans. In fact, 99% of the pancreas is made up of exocrine cells, that is clusters of acini, whereas 1% of the cells are endocrine in nature and they form the islets of Langerhans. Now, this islets of Langerhans, it produces four different type of it in fact contains four different type of cells within it. It's a group of cells called as islets of Langerhans, and it contains four different type of cells. Alpha, which produces glucagon, beta cells which produce insulin, and then gamma cells which produce the pancreatic polypeptide, and the delta cells which produce the somatostatin. Right. Now gamma cells are also called as the F cells. In fact, alpha cells make up of 17% of the islets of Langerhans. Beta cells make up the 70% of islets of Langerhans. The delta cells make up 7% of the islets of Langerhans, and the rest 6% is made up of the gamma cells. Now, glucagon and insulin, they are two hormones which are opposite to each other. They have an antagonistic approach, and both of them are known to control blood sugar. They are known to control blood sugar, but they are just having opposite effects. So let us see how that happens. Start with having a condition. We will call this condition as hypoglycemic condition. In the body is showing hypoglycemic condition. Okay, just a second. Yeah. Hypoglycemic condition basically means low levels of sugar in the blood. Low levels of sugar in the blood results in this hypoglycemic condition. So when this condition is established, so there is this signal that goes to the hypothalamus, right? From there it goes to the pituitary gland, pituitary gland, and the pituitary releasing hormones or the stimulating hormones or the tropins, they finally reach the islets of Langerhans of the pancreatic cell. They reach the alpha cells of the islets of Langerhans and then this islets of Langerhans produce glucagon. So this is one part. So what I'm going to do is I'm going to remove everything and I'm just going to start with glucagon directly. Okay, so I'm going to just remove all of these multiple steps. This is just to remind you of what is happening. I'm going to remove all these multiple steps and I'm going to directly go with the formation of glucagon. So here I'm going to directly write glucagon formation, or there is production of glucagon. So there is glucagon that is produced. Now, what happens to this glucagon? This glucagon first goes into the hepatocytes. It directly goes and acts on the adipocytes and the hepatocytes. Adipocytes and hepatocytes. Okay, so adipocytes are the tissues that store food that fats, and hepatocytes are the cells of the liver. So it is acting on the adipocytes and hepatocytes, and once it goes there, that is into the liver cell, it starts two different functions in there. So what it does in the body, it will start in the liver of fat cells and on the fat cells and on the hepatocytes. What it does is it starts to take two different functions. It carries out two different processes, or it initiates two different processes. What are those functions? The first process that it initiates, it's called glucogenolysis. It's called glucogenolysis. And the second process it initiates is gluconeogenesis. Gluconeogenesis. Okay, what I'll do is I'll just write it in even more. I'll just write everything in a little concise space because this is taking too much of space. Okay, so axon, and it starts a process called as glycogenolysis and gluconeogenesis. Now, what is glycogenolysis? As the name itself says, it is a process where glycogen is converted into glucose. Right, and gluconeogenesis is a process where amino acids or proteins and some basic fats are used. Amino acids and fats, they are used to produce glucose. So two processes, and both processes there is formation of glucose. So what this will do? This is basically what is doing is both these processes, they are carrying out the release of glucose. Both of these processes, they are carrying out the release of glucose. And where is this glucose entering? This glucose will now finally enter into the bloodstream. Glucose will finally enter into the bloodstream. First, it will reach hepatocytes. It will finally reach the hepatocytes. And from the hepatocytes it will reach into the bloodstream, and once the glucose levels reach into the bloodstream, there will be the return or restoration of homeostasis. Right, so this is what happens when there is hypoglycemic or low blood sugar conditions, and where is the release of your glucagon hormone. Now, when the conditions are reversed, means when there is a hyperglycemic condition, when there is a hyperglycemic condition, that means when there is excess of glucose in the blood levels have more amount of glucose, then you have the production of insulin from the beta cells, and this insulin will directly act on various cells including the hepatocytes. Now here what it will do by acting on various cells including the hepatocytes, it accelerates the diffusion of glucose into the cells. It accelerates diffusion of glucose from the bloodstream to the cells, because ultimately the glucose has to reach the cells, right? So what happens is more amounts of glucose are directly going into the cell rather than moving into the bloodstream. Then insulin further it goes into the hepatocytes, it acts on the liver cells, on the hepatocytes, and it starts two processes. One is it starts glycogenesis. Now this process literally means conversion of glucose to glycogen. Okay, then it will also create another process called glucolysis. Sorry, not glycose, gluco. Yeah, glucolysis, which is breaking down of the glucose in the body, right? So one, it is converting glucose into glycogen. Second, it is creating glucolysis. Third, it is promoting lipogenesis, which is formation of fatty acids, right? So all these three, by doing these three, what it is doing, it is preventing, so it starts these steps, we'll write it like this, it starts these following conditions, and it is preventing, what is it preventing? It is preventing gluconeogenesis that we have seen in the hypoglycemic condition, and glycogenolysis. So both these steps are prevented, and these three steps, that is glycogenesis, glucolysis and lipogenesis, are created. Now this, it results in what? It results in the failing, or it results in the decrease of blood sugar. It results in the decrease of free glucose in the liver or in the hepatocyte. So there is no more free liver that will be moving, free glucose that will be moving in the liver cells. This results in the fall of or decrease of blood sugar levels, and we reach a homeostasis, or a homeostasis is restored. Now, so if I have to sum up the whole thing, blood sugar levels, okay, if they increase, which is when they reach the hyperglycemic condition, hyperglycemia, you have the production of insulin, okay, and this insulin, it creates glycogenesis, okay, and it inhibits, or rather we will write it like this, it inhibits gluconeogenesis, and basically what it is doing, it is decreasing the sugar levels in the blood, or glucose level in the blood, and finally you are making sure that it is reaching in the homeostasis. If it is ulta, that means if there is a hypoglycemic condition, if there is a hypoglycemic condition, then what is happening here? Glucagon is produced. This glucagon will carry out the gluconeogenesis and glycogenolysis. Both the cases will result in increase of glucose levels in the blood and basically restoring the homeostasis. So that's why we say that insulin and glucagon are antagonistic in nature.
For more content, like, share and subscribe to www.i-win.in.